Okay, so my name is Jeff Niemann. My background is in civil and environmental engineering. I'm currently a professor at Colorado State University, and at CSU I coordinate the Water and International Development Program. I also teach a graduate class on water engineering for international development. I've been involved for several years with EMI as a volunteer. I've participated in several projects over the years. I've also been involved in some projects outside of EMI internationally. Okay, so the scope of this session is really focusing on the fact that civil engineers are often asked on EMI trips to make an assessment of the water quality for a client ministry or a community. And so what we're aiming to do in this session is, first of all, talk about the importance of water quality, why it matters, the most relevant water quality properties, and then methods that we can use to assess water quality out in the field. And let me say that this presentation is primarily intended for civil engineers who maybe don't have a lot of experience in this area, haven't gone on an EMI trip before. But my hope is, if you're a non-engineer, that you'll also gain some insights on this topic. Okay, so let's start with the big question. Why is water quality important in the first place? Well, the World Health Organization has what they call the drinking water ladder. And essentially what they do is they break up everybody's water supply into 5 categories. At the top of the ladder is what they call safely managed water supplies. These are water supplies that should be safe for consumption, and they're also piped onto the premises of households. Down a notch is the level that they call basic. And to be in that category, the water supply is an improved source, which means it has the potential to be safe. It doesn't necessarily deliver safe water, but it has the potential to do so. And it also has to be within 30 minutes round trip, including wait times. Below that is the limited level. This is still an improved source of water, but in this case, it's at a distance that's greater than 30 minutes or a time. And then below that is an unimproved source, which is essentially an unprotected well or spring. And below that is just consuming water directly from a surface water body. So this pie chart shows the breakdown globally of how people access their water. And what you'll notice is 11% of the world's population falls into the yellow, orange, or dark orange categories, which means we can pretty much be assured that their water supply is not safe for consumption. And overall, 30% of the world's population falls outside of the safely managed category, which means that it's possible or likely that their water is unsafe for consumption. And of course, a lot of those folks who are in those categories are in the majority world, and a lot of EMI clients, ministries, and communities are certainly at risk of being in those categories. So of course, that raises the big question: what are the most important characteristics to consider when evaluating the safety of drinking water? Well, we can actually break down the characteristics into 2 categories. The first is what we call chemical characteristics. The second would be the biological characteristics. So the chemical characteristics include all the minerals, the salts, the chemicals that are in the water. And some of those have health impacts, but in most cases, those attributes of the water primarily affect the acceptability of the water. And by acceptability, we mean the aesthetics of the water and also just the usability of the water for washing and other purposes. So according to the World Health Organization, the most important chemical attributes for health are arsenic, fluoride, nitrate, and nitrite. And on this slide, you can see the health impacts that can occur if the levels of those chemicals are too high in the water. And also listed on the slide are the maximum concentrations that are acceptable according to the World Health Organization guidelines. Now, of course, as I said, most chemical characteristics are important primarily for the acceptability of the water. And again, according to the World Health Organization, these are the most important characteristics for determining acceptability. So iron and manganese, both of those affect the taste of the water and can also lead to staining of clothes. The pH of the water, of course, affects whether it's acidic or basic, so how reactive it's likely to be. If you're far away from neutral conditions, it can lead to corrosion. Also, if you have high pHs above 8, it can reduce the effectiveness of chlorine disinfection. Hardness describes just the amount of calcium and magnesium ions that are in the water. It can lead to taste problems at high concentrations, and also it can lead to scaling, as you see in the picture on the slide. The white is where water has discharged and left residue from the high hardness of the water. And finally, turbidity just describes the cloudiness or really the light scattering properties of the water. And it mainly affects the appearance of the water. And also, if you have high turbidity levels, it can affect the effectiveness of the chlorine disinfection and other strategies for treating the water. Okay, so how can we actually measure these characteristics out in the field? Well, a lot of these characteristics can be measured using just simple test strips. So arsenic, nitrate, nitrite, iron, etc., pH, these are all things that are readily measured with test strips. And so typically all you have to do with these test strips is just run a little bit of water over a little strip. There's a little pad that will change colors, and then you have to match the color of the pad to a scale that's on the bottle, and that will give you the results. So a couple of limitations to know about test strips. The first one is that you can only get certain outcomes. So for example, on arsenic, there's 6 numbers that you can get as a result from a test strip. And so that means the results are not very precise. Another challenge in dealing with test strips is the fact that people see colors differently. And so that can lead to inconsistencies and inaccuracies. And a kind of interesting innovation in recent years is the use of apps on phones to improve the reading of test strips. So there's some applications out there that you can use your camera to take pictures of the test strip, take pictures of the scale on the bottle, and objectively match those colors. So there are more specialized tests out there for fluoride and manganese, so a little bit more in-depth testing needed for those. And sadly for turbidity, the old-fashioned method of using a Jackson turbidity tube is not really precise enough. The sensitivity of that test isn't high enough to measure the turbidities that are most relevant in water quality assessments. So probably the best tool for that is the use of a turbidimeter. Sadly, those run $350 to $600. So there's not a real inexpensive way of evaluating turbidity. Okay, so let's turn our attention to biological characteristics of the water. So when we talk about biological characteristics, we're primarily thinking about viruses, bacteria, protozoa that are living in the water. And to some extent, we're also concerned about worms that might be in the water. And the biological characteristics are the ones that are the most important for health because it's these characteristics that lead to the major waterborne diseases and also just the broad collection of dysentery and diarrheas that can occur. If you're not familiar with biological water quality and these waterborne diseases, an important thing to understand is that you ultimately get these diseases by consuming water that's contaminated, at least microscopically, with feces. So when somebody has one of these pathogens in the body, they exit the body through the wastes. And then if somehow you end up consuming water that's contaminated by those wastes, you end up getting those waterborne diseases. And in fact, feces can take multiple pathways to make people sick, as shown in the diagram you see there. But water is an important one of those pathways, whether it's consumed directly or whether it's by the route of food. Okay, so how do we go about assessing the biological quality of water? Well, traditionally, an indicator of biological water quality has been total coliform. So total coliform are useful because they do live in the intestines of humans, also in warm-blooded animals, but they are also found out in the environment in places that are not necessarily associated with intestines or some sort of contamination. So they were historically used because they are found to some extent in the intestines of humans. Therefore, it does sort of potentially indicate some connection to fecal contamination. And also generally they're easy to culture, easy to grow. But in the past 10, 20 years, there's been increasing research that actually shows that total coliform has a very low correlation with the occurrence of waterborne illnesses. So just because there's coliform in the water doesn't necessarily mean there's pathogens in the water. And as a result, total coliform are really viewed now more as an indication of just the general cleanliness of the water and the integrity of the system. And I think by integrity, they're not talking about the moral fiber of the system. They're really talking about how isolated it is from the environment. So again, coliform now are not so much viewed as a direct indication of waterborne diseases or pathogens. They're really just a broader indication about the biological water quality. Another indicator that's broadly used and more commonly used these days is E. coli. So E. coli is a subclass of coliform bacteria. So within that broad class of coliform bacteria is the subclass of E. coli. And it turns out that a large portion of coliform that come from the intestines of humans are E. coli. So E. coli is a much better indicator of fecal contamination than coliform overall. And in fact, E. coli also doesn't live very long outside of the body in the environment. So if you're seeing E. coli in water, it's a pretty good indication that you have a pretty direct connection to fecal contamination. Now, that being said, most strains of E. coli are still harmless, but some E. coli do actually cause waterborne illnesses, and in particular, severe diarrhea. So these days, E. coli is really the preferred indicator organism for the biological quality of water. But that being said, it's also now recognized that just because you have a lack of E. coli in the water doesn't mean you have a lack of other types of pathogens. So it turns out that viruses and protozoa in the water are also, they also have a low correlation with the presence or the number of E. coli in the water. So really the optimal approach, I guess, these days would be to use multiple indicator organisms to assess the water quality. But I think there's still a heavy reliance of E. coli, particularly in the applications that we're talking about today. Okay, so those are the indicator organisms. What are the requirements that should be met for the water to be safe? Well, the most recent World Health Organization guidelines that I've seen are the 4th edition, which I think came out in 2017. And again, these guidelines are really trying to push people towards the use of multiple indicator organisms. But for E. coli, they're pretty clear that you should never be observing E. coli in the water. Any sort of presence of E. coli would be considered an indication of possible pathogens. I do think it's useful, though, to look back a few editions of the guidelines to when coliform was included as an important indicator of whether water was safe to drink or not. Since we can still measure coliform out in the field, it's helpful to have some understanding of how much coliform we might want to be seeing or not seeing in the water. So also on this slide, you'll see from the second edition of the World Health Organizations, they still say that no samples should have E. coli, but they also say that the presence of coliform should be rare, and when there is coliform in the water, there shouldn't be a lot of it. And it shouldn't persist through time as well. And I still think it's useful to have those guidelines in mind. Again, it's just a broad indicator of the water quality. Okay, so how can we go about assessing biological water quality? How do we assess that out in the field? Well, typically we use two strategies. The first one is just an analysis of a water sample. So the idea here is we're going to take one or more samples of the water. We're going to make measurements on that water sample to get direct assessments about the presence or absence of these indicators, or potentially the number of indicator organisms that are in the water. Now, the problem with that approach is that it only gives us an indication of the water quality where and when we took that sample. And oftentimes contamination can be intermittent and localized, so it doesn't necessarily tell us broadly what's happening about the water source or the water system we're evaluating. So the other strategy we tend to use is the sanitary survey. And really what this is just a common sense inspection of the system, the source, the community, to identify potential sources of contamination of the water. And also a good supplement to that field inspection is interviews of community members, the operators of the water system, to get to learn from what they've learned about the system. And really the purpose of the sanitary survey is to extrapolate what we learned from those water samples to get a broader sense of what's going on with that system. So hopefully it'll give us a more holistic or comprehensive view of the water quality. Now, I want to be clear that I think the best approach to take with this is not to view number one there and number two as competing or alternative strategies, but really to view them as complementary strategies that we use together. What I want to do is just try to do a little bit of an example sanitary survey here. And I just want you to take a look at the pictures and see if you can spot some hints that the water source might be biologically contaminated. So take a look at the picture on the left there. We see some folks washing clothes. They're next to a stream. What might be the issue there that might cause some concern about contamination? Yeah, washing diapers, washing clothes. So anytime we see people in contact with the water source, we know that there's a risk of contamination. We pretty much assume that we have bacteria on our bodies all the time. So if we're coming in contact with the water, there's a risk that that bacteria, those pathogens, are going to get into that water source. So the picture on the right, that one, so let me describe it first. So what we have going on there is in the background, there is a pump house. And in the tall grass in front of that is a drilled well. And so the concern with that one is actually the fact that we have waste disposal, solid waste disposal in this case, is occurring right next to the source. So again, what we have is a potential source of contamination right next to our water supply. So both of these are what are called hazard factors by the World Health Organization. And what they mean by that are these are just sources of contamination that are located right next to a water supply. So that's the concern. So on the left picture, what you're looking at there is a transmission line, and it is entering into a community storage tank. So are there any hints here that might lead us to believe that that water could be biologically contaminated? But the concern here is the fact that we have an open tank. There is a gap between where that water line enters and where the top of the tank is. The tank is open to the environment. And if it's open to the environment, we could have birds flying in, we could have bats going in, and they could be defecating in the water. It could be unclean. All right, the picture on the right there, that's just a zoomed in view of a little distribution line that's gotten exposed. Looks like it's been wrapped with some tape. What's the possibility for biological contamination there? Negative pressure at the repair of the pipe. So essentially the concern is if you have water getting out of a pipe, there's always the risk of water or any kind of contamination getting in. And that's especially concerning if the water is below atmospheric pressure. We could have water entering into that pipe. So both of those are called pathway factors. And that's because what we're looking at are pathways for pathogens to be entering into the water supply. All right, so on the left, we see some kids. Actually, this is in Belize. It's the last day of school. They've sanded down their desks. They're varnishing them for the next grade. And in the background, the white fence structure is a wellhead. So I'm going to make this one tough for you. Of course, the use of the chemicals right next to the well is a concern, right? We don't want varnish entering into the groundwater. But let me ask you this. If the kids weren't there, would we still be concerned? Like, take the kids and the desks out of the picture. Is there still a concern there? Really what we're concerned about here is just the proximity of activity to that well, the lack of fencing. So just because there's no fence around the source area for that well doesn't necessarily mean there's a problem, but it could lead to it. The picture on the right I'm going to make hard for you too. So clearly there's a woman collecting water from a surface water body. We know that is likely to be unclean. But imagine instead she was collecting it from a tap. Would there still be any cause for concern, anything we might want to notice that we might want to pay attention to? So in this case, the open collection vessels is also potentially a concern. So these are what are known as indirect factors. And indirect factors are things that are not necessarily problematic on their own, but they're factors that could lead to pathways or hazard factors developing in the future. The other tool that we use is the analysis of a water sample. And I want to just summarize 6 different tests that are out there. These are just tests that I'm familiar with and I've used. They're tests that I think overall I can recommend. There may be other good tests out there as well, but these are ones I think are useful. So the first test that's here is produced by the company Hawk. That's just the version I've used. Other companies prepare very similar tests, so don't feel like you have to buy it from that company or that I'm recommending that particular brand. Anyway, Hawk calls it the Pathoscreen test. And this test is really easy to implement. Essentially, you just take a 100 milliliter sample of the water in a bottle or a Whirlpack bag. And then you just need to add a nutrient powder to the sample and you seal it up. All you need to do is store it for 48 hours. And if it turns from yellow to brown over that time, that indicates that there is this broad class of what we call hydrogen sulfide producing bacteria present in the water. So advantages of this test are, first of all, among all the tests I'm going to talk about, it is the cheapest. So it costs about $2 US per sample, which again is the cheapest among the tests I'll describe. Another good aspect of it is that it does have a relatively large sample size. It's 100 milliliters. And I'll talk later on about why that might be important. Another convenient thing about it is that it doesn't require incubation at or near body temperature. You can allow the sample to sit out at room temperature during that 48 hours. Disadvantages are that it only considers this really broad category of bacteria. It only tells you if there's presence of hydrogen sulfide producing bacteria. And so what that means is if that sample turns brown, really it just tells you some amount or some type of that broad category are present. It doesn't mean you have coliform, it doesn't mean you have E. coli, it doesn't mean you have pathogens. So really a brown result isn't all that diagnostic or helpful for describing the water quality. However, if it stays yellow, that means you don't have this broad class present, and so that's a little bit more diagnostic. You can have some confidence that there are not pathogens in the water. The second test is again produced by Hawk, and others have similar tests. I call it the Hawk MUG test. MUG is an acronym for a chemical that you use in the test. The one I'm going to describe is actually, it starts with the liquid in the bottle, but there's alternative versions that use a powder instead. So the idea here is you start with a bottle that just has a small amount of this kind of scarlet colored liquid at the bottom. And you just fill up the bottle with your sample up to a fill line. I think it's about 100 milliliters, but it might be a bit less than that because there's some liquid in there to start. So anyway, all you have to do is keep that. You do have to incubate it at body temperature for 48 hours. And if the color changes from red to yellow, then that tells you that some type of coliform are present. And then as an additional step, if you use an ultraviolet light and you shine the ultraviolet light on it and it fluoresces, so the sample turns kind of that milky white color that you see in the bottom picture, that indicates that E. coli are present. So again, we're not getting any kind of numbers here, but we're getting presence, absence. So advantages of this test is that it does directly evaluate coliform and E. coli, and it does consider a large sample, 100 milliliters. But it does have some disadvantages. So first of all, it's pretty expensive. It's about $6 US per sample. It does require incubation, which can be difficult out in the field to make sure you're keeping it at the right temperature for that 48 hours. Another challenge is the indicator we care the most about is E. coli, and you've got to have that ultraviolet light in order to assess the E. coli. And then finally, it doesn't give us any counts. It just is a presence-absence test. So we really don't have an understanding of the extent of contamination from this test. The third test is called the Aquagenix compartment bag test, or CBT test. And this one's also pretty easy to do. You take a 100 milliliter sample in a Whirlpack bag, and then you just pour in a nutrient powder into the sample. And by the way, in that top picture, you probably shouldn't have the nutrient powder inside the bag because the outside of the powder could have bacteria on it and you're trying to keep that bag sterile. But anyway, you just add that nutrient powder to the bag. You seal it up. Well, I'm sorry, you don't seal it up. So once you've added it, you need to mix the powder in, get it good and dissolved. And then what you do is you pour that sample into a compartment bag. And that's what you see in the middle picture of the slide. And the compartment bag just has 5 different compartments that have different sizes. And essentially what happens is it does a presence-absence test in each of those compartments independently, and it aims to use the results from those compartments to give you a most probable number of E. coli. So anyway, once you add the sample to those compartments, you have to wait 48 hours. Again, you don't have to keep it at body temperature. And then an interesting thing about this test is after you conduct it, if it changes from its initial color of yellow to blue, that indicates the presence of E. coli in that compartment. And then you can also use the ultraviolet light to determine if you have the presence of coliform, other types of coliform. And as I mentioned, the specific pattern of blue and yellow compartments that you see will give you that most probable number estimate for the E. coli in your sample. So advantages of this test. First of all, it does evaluate directly coliform and E. coli. It considers, again, a large sample, 100 milliliters. It doesn't require incubation, although you can if you want to. And it provides an E. coli count. So it's the first test we've talked about that does that. It has some disadvantages too, though. First of all, it's very expensive. It's about $9 per sample. So that's pretty steep. And also, I found that compartment bag to be pretty difficult to use. First of all, those compartments are pretty much sealed when you get the bag. And so you have to kind of rub the sides together to get all the individual compartments to open up before you pour the sample in. And it can be difficult to get those compartments to be open. Then you have to roll down the bag and seal the compartments off from each other so that the tests are independent. All of that can be kind of tough to do. And then finally, it does not provide any kind of count for the total coliform, just the E. coli. The fourth test is the Petrofilm test from 3M. So the way you do this one is you buy these little cards, which have the little pink circle on them and a vellum that is on top. You just add 1 milliliter of water to that nutrient cycle, that card, with a pipette, disposable sterile pipette. Once the 1 milliliter is on the cycle, then you just carefully roll the vellum down. You got to be careful to not trap air in there. And you also want to distribute that water as evenly over that pink circle as you can. You can buy spreaders. That's the plastic device you see in the picture. They've changed the style of the spreader from that picture. That just helps you. It's just a light, flat piece of plastic that helps spread the water out. I've found those to be not necessary, and they're quite expensive, so you can probably skip that, especially if you're experienced with this test. Anyway, once it's sealed up, it solidifies, it forms a seal between the vellum and the card in just a few minutes. Then you have to keep it, again, at body temperature for 24 hours. And after that, when you see blue colonies with gas bubbles associated with them, those are E. coli. Red colonies with gas bubbles are other coliform. So advantages of this one, it's pretty cheap, $3 US per sample. And I should mention, by the way, these costs are sometimes a little hard to calculate because, if you have an ultraviolet light, how do you allocate the cost to that light? So you should take these as just approximate estimates, just to give you a feel for the cost. It does evaluate coliform and E. coli, and it also provides counts for those coliform and E. coli. Disadvantages, it is a small sample. We're testing only 1 milliliter of water. And again, I'll talk about why that matters in a bit. And it does require incubation. The fifth test is from Micrology Labs. It's called the Coliscan Easy Gel test. And this one starts with a little bottle that has a gel in it. And you add 1 to 5 milliliters of water to the gel bottle. You swirl it around to get the gel and the water well mixed. And then you pour the combination of the water and the gel into a pre-treated Petri dish. So this is not an ordinary Petri dish. It's somehow pre-treated. I'm not sure exactly what they've done to it, but it is a special Petri dish. The gel takes about 45 minutes to solidify. And then after 48 hours, purple colonies that you observe are E. coli, and pink colonies are other types of coliform. Advantages, again, this is fairly cheap, about $4 US a sample. It evaluates coliform and E. coli. It requires no incubation out in the field, and it provides counts. Disadvantages, it's a small sample, again, 1 to 5 milliliters. And one big challenge I've had with this test out in the field is that it is sensitive to movement. You really do have to keep it still for those 45 minutes while it solidifies. And also, even after that, I found that if you're hiking around with it or it's in a vehicle being driven around, the movement can lead to blurring of the results and it can make those colonies hard to count. So that's something to be aware of. And then finally, the counts can be somewhat difficult to make because the gel is somewhat three-dimensional. You can actually have colonies on top and below each other, which can make the counts difficult in some cases. The question was, can you buy all of these tests individually? And the answer in most cases is no. There are organizations out there that will buy sets of them and will sell you individual ones or perhaps donate. But in most cases, you have to buy groups of these tests together. And it varies test by test. So for example, the Aquagenix, they pretty much sell you everything you need for that test all as one package, which is nice. Other tests, you have to make sure to buy your Whirlpack bags separately from your mug bottles, and they're sold in different amounts. And so that can be quite inconvenient. And in some cases, the number of tests is pretty large. Like I believe Aquagenix sells them in a pretty large package these days. So good question. Okay, the sixth test is again from Hawk. It's the membrane filter test. And this one I like to call the Tesla of tests. It's, I think, the kind of the highest end in terms of the quality of the results. This test starts with what's called a membrane filter unit. If you look at the top picture on that slide, pretty much everything in the person's left hand is the membrane filter unit. And what's in the right hand is a hand pump. So the way you do this test is you pour 100 milliliters into the top compartment of that filter, and then you use the hand pump to create negative pressure in the lower compartment, and that will suck the water through the membrane filter, which is just a white disc you might see between the two compartments of the picture. As the water goes through the membrane, the water passes through it easily, but the bacteria cannot pass through, so they all get collected on it. Then you pull apart the two halves of the unit. You use sterile forceps to remove the membrane. You put it into a Petri dish with growth medium. Then you have to keep it at body temperature for 24 hours, and then you can count colonies. Blue colonies are E. coli, red colonies are other types of coliform. So advantages of this test. It evaluates coliform in E. coli. It considers a large sample. It provides, I think, the most reliable counts for two reasons. One is this membrane is two-dimensional, so you don't have colonies on top of each other. And also by sucking the water through that membrane, the water passes through very uniformly, so you don't get clustering of the colonies like you might get with the Petrofilm test. So I think it'll give you the best counts. Disadvantages. It is the most expensive among the tests that I've talked about. It's about $14 per test. It's got bulky equipment. You have to have the hand pump and these large filter units. Those are disposable. So for every sample, you have to have the whole filter unit. And it does require incubation. So since incubation is required for a number of these tests, it's worth talking a little bit about how you can do incubation out in the field. A common way to do this is just to keep the sample on your body for the whole incubation time, but that can be kind of hard to do with bottles, and it's also pretty just inconvenient. So I wanted to mention a low-cost home-built incubator that was developed by Bill McNeil. He's an EMI volunteer, and he had, I think, a great idea. So what he does is he just takes a U.S. Postal Service priority mail box, which you can get at the post office here in the U.S. for free. You can lay it flat in your luggage when you travel. And so that forms the shell of the incubator. and then to provide the heat inside the incubator, he's using just a seed starter mat. So that just produces heat. The benefit of using the seed starter mat in comparison to, for example, a light bulb is the light itself can actually affect your results. So here you get the heat without the light. And he's also found that it maintains about the right temperature in a relatively cool room. And what's going to actually control the temperature of this incubator is the wattage of the seed starter mat compared to the surface area of the box you use. And I suspect you could poke holes in the box to lower the temperature too, if you wanted to. Okay, another question is, where should we collect the water samples? So let me give you an example from an EMI project. So the gray map you see on the left there is a school campus in Belize, K through 12 school. And this campus actually has two water sources. They call them the primary well and the backup well. You can see that both of those labeled on the map. The picture on the slide shows you the primary well. And on the next slide here, the picture shows you the backup well, which actually you saw another picture of earlier. So those are the sources. From there, the water goes to a tablet chlorinator. This is an inline chlorination unit. And after it passes through that, which is the red diamond on the map, it goes to some storage tanks. There's about 4 storage tanks. And then from there, it goes out to serve the campus. It goes to a kitchen, and it goes to buildings essentially with sinks or bathrooms. Where should you take samples if you were going to try and evaluate the water quality for this campus? So first of all, current and potential sources are great. And in fact, we did that. And at the primary well, what we found was no bacteria. And at the backup well, we actually found the presence of bacteria in this case. After treatment is another good place to do it. So we took a sample after the water had passed through the chlorinator, spent some time in the tanks, and actually we found that there was still presence of bacteria in this case. Another good place to take samples is priority locations. So this is places where we really need the water to be clean. So for example, on this campus, the kitchen is a primary location because it's a place where it's probably most likely that the water would be consumed. And in this particular example, we found that the bacteria were still present at that location. And then a final place is the most distant points in the system. So in this case, that was the high school bathrooms. And again, we found the presence of bacteria there. So I do want to mention that that also you want to consider, when I say most distant points of the system, in some cases that might not actually be the water system itself. If a community has public taps and the community members carry the water to their homes and store it there, that would be your most distant point of the system. So that's where you would probably want to take those samples. And then of course, any kind of suspected problem areas, places where you have low pressure in the pipes, leakage, negative pressure, those would also be good places to sample. Okay, the final thing I wanted to mention today was just a little bit about interpreting the results. So if we get positive or negative results, I mean, what do we really make of those in the bigger picture? So I wanted to share a series of experiments that we did in my class this fall. So all of these tests that we did of biological water quality were conducted at the same time for the same source of water. It's just a pond on the campus of Colorado State University. You see it in the background of the picture on the slide. The pond has emerging groundwater. It probably also has stormwater coming into it. And we fully expect that pond to have lots of coliform in it and probably also some E. coli. There's geese, there's dogs, there's people coming in contact with it. So what we did is we implemented 4 out of the 6 tests that I described today. And for each of those tests, we conducted between 24 and 30 trials. And by the way, the reason the numbers are different for the different tests is because you buy them in different amounts from the manufacturers. So we performed those tests. My students were deeply involved in the process, and I surveyed the students, and we figured out which tests were properly incubated or not. We discarded the results for the ones that we felt weren't properly implemented. So first, let me just describe the results that I personally got for the Aquagenix test. You see it again shown at the bottom of this slide. You can see that I had 3 compartments that showed the presence of E. coli, they're blue, and 2 did not. So from that, you can read a table with the instructions from the manufacturer, and it tells you that the most probable number of E. coli in this water source is 14 per 100 milliliters. Now, what's interesting is this pie chart shows the breakdown of results that we got from all the Aquagenix tests that we performed. And specifically, it's showing you the number of compartments that showed the presence of E. coli. So my particular result fell into the yellow wedge with 3 compartments. But what's interesting is you can see a fair number came up with 2 compartments. And actually, 31% of the tests came up with no compartments showing the presence of E. coli. So it's important to recognize that if you take one test from a source, it's not necessarily what you're going to get if you take an abundance of tests from that source of water. Okay, so let's look at some of the other results we got. So these are the results we got from the Hawk mug test. And here I'm not talking about E. coli. I'm just talking about the presence of coliform. So out of all the tests we ran, 14% of those tests showed the absence of coliform. Now, we don't know definitively that this source has coliform in it, but given its nature, it's a pond, there's lots of contact with animals and humans, we fully expect there to be abundant coliform in that source. So I would view that 14% as being most likely false negatives from that test. Looking at the Petrofilm test, of course, this gives us also counts, but here I'm using it just as a presence-absence test. And in this case, 23% of the tests showed an absence of any coliform. Again, I would suggest those are largely false negatives. The next test was the Coliscan Easy Gel. And again, you can get counts from this test. On the bottom left, I'm showing you just whether or not we observed coliform in general. And for that test, 33% of the tests did not show the presence of coliform at all. The final chart on this slide just shows the results from the Coliscan test for the E. coli. And these results, I think, are actually pretty interesting. So it shows that 92% of our tests had no E. coli present. But if you go back to the Aquagenix tests, remember we said there were only approximately 14 E. coli per 100 milliliters. Well, the Coliscan test is only a 1 milliliter test, which means we should only observe E. coli in 14% of those tests, if there's really 14 E. coli per 100 milliliters. So actually, these Coliscan E. coli tests are pretty consistent with that. So overall, if we back up, just overall, I think it's important to recognize there's a significant chance of false negatives and diversity in the results that you get from these tests. There could be false positives as well. I think that would be most likely due to you contaminating the sample inadvertently. So for example, the powder bag I mentioned being inside the sample bag, that could introduce bacteria into the sample that's not really in the water. So you really do have to be super careful not to touch the lip of the bag or anything that might contaminate the sample because that's the most common way to get a false positive. One final word about that little experiment. This is just a collection of pictures from the tests that I personally did. And what you'll notice here is that all the tests that are 1 milliliter tests, the Coliscan and the Petrofilm, in my case, came up with the absence of any bacteria. The tests that were 100 milliliter tests, whether it's the Hawk mug test or the Aquagenix test, both of those came up with presence of both coliform and E. coli. So this is why I think the size of the sample matters. Those small 1 milliliter samples, you can miss things. So let me just wrap up by saying some final thoughts here. First, I want to say that the type of test that you do matters. The 6 tests I talked about today, I think, are all reliable, good tests to use. But there are other tests out there that I don't think are very reliable. So it's important which one you choose. Also, I think the sample size matters. Larger sample sizes, I think, are going to give more reliable results. I didn't talk about this, but also the storage of the media before you do the testing can also matter. These tests have shelf lives. Some of them need to be refrigerated or frozen during storage, so that's also important. Incubation matters. In previous years of my class, we've tested different levels of incubation for the tests that say they require it, and we found that that also affects the results. I mentioned this earlier, the movement of the Coliscan Easy Gel matters. And also another aspect of it is you want to keep it out of the sun. So while you're waiting 45 minutes for that to dry, it's easy to just have it set out in the sun, but that can potentially irradiate the bacteria and halt their growth. So I know it's a little overwhelming. I just told you all these things matter and you have to be careful. Let me just close with a couple of constructive thoughts, I guess. First, I suggest you use multiple tests. So for example, a good practice might be to use a 100 milliliter presence absence test and then a 1 milliliter test for your counts. Also, don't be overconfident in your results. Recognize false positives and negatives do happen. There's limits on what even the presence of coliform E. coli tells us. And then finally, I think it's really important to share your results in a constructive manner because it can be sort of overwhelming and confusing to a ministry because they're not familiar with all the limitations of the results when they get it. What are the disposal requirements for the microbial tests? Anything special required? That's a good question. They all have essentially the same disposal requirements. You essentially add a little bit of bleach or chlorine to the test to halt the growth. And you have to give it some time to halt the growth. And then if it's a liquid type of test, usually you can just pour it down the drain. If it's a solid kind of thing, you can throw it away. Out in the field, I typically throw everything away rather than putting it down the drain because of septic systems and all of that. And also, it's worth mentioning that these tests stink. Some of them really stink. So you definitely want to dispose them in an outdoor trash container that won't come into contact with people and so forth. How do you keep the Petrofilm test at body temperature? And mainly, how do you keep the sample from getting contaminated? So the Petrofilm is designed to form a seal around the little pink circle. I forget the exact time, it's like 5 minutes. So it should seal and prevent contamination. You can slip those into a pocket because they don't leak after a while. It's good to keep them like in a Ziploc just in case. A lot of times, if you're working in a tropical environment, it's plenty warm just to leave them setting somewhere. So oftentimes that's adequate. Why is E. coli count important if WHO states that any E. coli means water is unsafe? Why is presence absence test not enough? It's a good question too. And it has to do with two things which are related. So the World Health Organization also has risk categories, which are associated with the number of E. coli. The more abundant the E. coli are, the more likely that you would get an infectious dose of that pathogen and get sick. So as the number goes up, the risk goes up, and consequently, it may inform our treatment decisions. Is chlorination alone enough, or do we want to chain a couple of treatment methods together? maybe talk on the sampling procedure example. If the water is chlorinated, you will need sample containers with thiosulfate to neutralize the chlorine. Yes, good points. And in fact, whoever wrote that, that's an excellent point about the thiosulfate, and I'll add to that. So thiosulfate comes in some of the Whirlpack bags. It's a little tablet, and it's there to dechlorinate the water before you do the test. That being said, some of these tests, I want to say it's the Petrofilm that you should look to test my memory. Specifically say you should not use thiosulfate with the test. So those sort of tests would be hard to apply if you have chlorinated water. About taking the sample itself, just to keep it brief, the things I will say is, first of all, you typically want to sample the water for bacteria first and then evaluate the physical characteristics second. And that's simply because you don't want to contaminate the water by analyzing the physical chemical characteristics first. Also, if you've got a very still source of water, you want to make sure that you take your sample below the water surface, because if the water is truly still, that thin layer of water at the surface might be irradiated, and you might not get representative results. So I want to thank you all for tuning in today.